Now, the same chi-test, or chi-squared test is what it's actually called. Oh, what I forgot to do I tell you this in a minute? Hang on. Oh, yeah, I'm going to tell you how it works in a minute. Okay, so that can be used with a variety of different applications, because what it does is it compares expected values with observed values. So you can actually do other things like comparing if you got sort of several things on different days and you want to know, could that be equal every day, or is there something different about Fridays or whatever? You could set up a uniform distribution where you've got the same number every day and you compare the actual values and see if that's significantly different. I haven't taught that one this year, and there was also one we used to do with M&Ms where you compare the proportion that the company says is of different colours, and then you take your packet of M&Ms and you count up your colours and you see how they are, and you see whether what you've got is what would have happened if the colours actually were as they say. Okay. So, it can be used for different things. So in Lecture 4.1, we looked at the idea of independence. And so chi-squared's looking at independence, but rather than just saying, is it different, it's saying, is there enough evidence that it's different? So that's the difference. So, and there were two aspects, urgency and size were not independent. We decided that there was a relationship between them. Because of the non-urgent jobs, so here's non-urgent, 300 over 400, 3/4 of them were small. But for the urgent jobs, 0.43 were small. And so you can see those two numbers there are a long way apart. So clearly there is a difference. But if that was sort of like 0.55 and it was 0.54, is that different or not? Overall, the proportion of small jobs is 0.6. So we can see that the non-urgent jobs are more likely to be small than are the urgent jobs. Now that could have been seen as a population of a sample, or a sample. And this is a thing, it's quite tricky for a lot of people, is the idea of a population or a sample. And unfortunately, you can't blanket say that something is a population or a sample, because it depends on what you're looking at. If we're only looking at the total jobs in 1 month, and that's all we care about, that is the population. We can say, in that month, the proportion of urgent jobs that were small was smaller than whatever it was. Yeah, well, I mean, we can say it for sure for that month. So that's because we had population data for that month. But if we say, okay, we're going to use a convenience sample, and that month we're going to say it represents all of the possible months that can occur, and now we want to see, is this enough evidence to say that this exists everywhere? So, now as I say, it's not good enough as the sample's not random. However, and this is another one of the true-false statements I think in 6b, is that people do statistical analysis on bad samples all the time. In fact, way more often than they are ever done on good samples. Now, I'm going to be a little political here, is that the national government, and their genius, has decided to bring in national testing of school students. And in New Zealand, and because it's been proven to be a really bad idea in America and Britain, they thought we can do it too. And so one of the reasons that we haven't had to do this is that we've had this thing called NEMP, the National Educational Monitoring Project. And what it does is it takes a sample of all students at certain years and it tests them, rather than the entire population, which then causes teachers to teach to the test and at the detriment of education. It just sees whether our standards are going up or down and how things are going. And how the sampling is done there is amazing. It's called multi-level sampling, where they randomly choose schools and then they randomly choose pupils from within those schools. And it's just so well done that it's got enormous validity. Now, somebody else who goes out and just takes, a sample of 20 kids from somewhere, you can't have the same sort of evidence of what's happening because the sample has not been taken as well. So that's one of the reasons I taught you about the different types of sampling, so that when you go to read a report, you can say, well, this was a really good sampling method, it's got good validity, or you can say, well, there's real possibilities of bias here, and so you can't really use it, or you can give it less value than you would otherwise. So though it would be nice, and statisticians can sometimes be a little bit precious and say basically, oh no, you have to have randomised controlled trials, double-blind, otherwise it doesn't count. Now this is all very well if you're dealing with plants or even with medicine to a certain degree, But in many other aspects, especially in business and in education, you can't do randomised controlled trials, which is the only thing you can use to prove causation. So what you do is you end up with data that isn't that flash, but you do it anyway, but you have to bear in mind that what you've got is limited by the quality of the data you've got. Okay, so let's have a look at this one. So we've got our observed values from small, large, urgent, non-urgent. And this is all the sums. And how it works basically is it takes the observed value 300 and the expected value 240, and then that observed value 100, and that expected value 160, and so on. It finds a difference, which in each case is 60, because this is not a good example, squares them, and then divides them by the expected value and adds that all up. And that's where the chi-squared value comes from. Then it looks it up in a table for you and gives you, in this case, 0.000. So when you do the chi-test in Excel, it's doing all of that. It's taking each one of these, finding the difference, squaring it, dividing it by the expected value, adding them all up, and then looking up the tables. So you don't need to know how that all works. You just need to know that it does.